Hello friends, welcome back. In the previous video we had discussed about the MOSFET to be used as a basic amplifier and that we should use it in the saturation region only. If you have not watched that video, please go and watch that video and come back to this video to learn about the voltage gain factors. Okay, so as we have seen that for a MOSFET to work, we have to connect it in this type of a circuit. This is the VDD, this is the R, and this is the MOSFET, where this is the source, this is the drain, and this is the gate terminals. Right. Here, what we have to do if we have to use this as an amplifier, first of all, we have to produce a DC gain, DC voltage, which is my VGS, and we have to give another AC voltage, which is also represented as my small VGS. Right. So, what do we know? We know that the current equation I, for which region do we have to use this MOSFET for an amplifier? That is a saturation region. So the saturation region current is mu COX W by L into VGS minus VTH whole square by 2. Right. So this is the equation that we get, where this is capital VGS, okay, RMS value. So here we are giving two values of VGS. So the equation goes to mu COX W by 2L, let's say, into V capital GS minus plus small VGS, right, minus VTH whole square. Clear? We just expand this VGS into the two corresponding parts. Now what we do is we separate it as capital VGS minus VTH together and plus VGS together. Okay, so we can expand it as mu COX W by 2L and like this, like VGS minus VTH plus VGS whole square. This is my A, this is my B. So we expand it as mu COX W by 2L into VGS minus VTH whole square plus 2 into VGS minus VTH into small VGS, right, plus VGS whole square. These are the three terms that we get, right? So we can expand it as mu COX W by 2L into VGS minus VTH whole square plus mu COX W by, this 2 gets cancelled, so W by L into VGS minus VTH into small VGS, okay, plus mu COX W by 2L into VGS square. Okay, so these are the three terms that we get. Now this term is a non-linear term for the AC gain. So we need to remove this term. To remove this term should be greater than this term, because this is a constant term, right? To neglect this term should be greater than this term. So this term should be greater than this term. So just comparing, that is my mu COX W by L into VGS minus VTH into VGS, that should be greater than the value of this one, that is my mu COX W by 2L into VGS whole square. Mu COX WL gets cancelled, 1 VGS gets cancelled, so my VGS minus VTH should be greater than VGS by 2. That is, to be precise, that is my VGS. That is my VGS value. Let me write in the next page maybe. That is my VGS value here should be less than twice my VOV value. Okay. This is the thing that we get, because we know that VGS minus VTH is my VOV, right? So following with that part, we can write that the current equation now is my I is equal to, so we should write the small I because now it's the RMS one. It's equal to mu COX W by 2L into my VGS minus VTH whole square plus mu COX W by L into VGS minus VTH into small v GS. Right, this is the equation that we get now. This is my DC part, and this part is my AC part. Right, so the AC current, we can write it as mu COX W by L into VGS minus VTH into VGS. We can write this. So from here we can get my ID by VGS, which is my transconductance, that is my GM, normally represented as is mu COX W by L into V capital GS minus VTH. This relation we will need it for a long time. Okay, going to the next thing, that is we have now found out my transconductance. Now we can write that is my drain voltage VD. Okay, my VD, it can be written as my VD, my VDS, suppose VDS plus small VDS, right? Now from this diagram we can say that my V capital DS would be equal to VDD minus IDRD, right? So this can be written as VDD minus, this is my IDRD plus VDS, right? This is equal to my VDD minus IDRD minus of IDRD plus VDS, right? Okay, so this VDD minus IDRD, this is the DC part, that can be written as my capital VDS, and this part that we get out here, that is because of the other part, because of the AC part. Oh, I'm sorry, one thing that should be that this is equal to VDS plus VDS. Here it won't be VDS because logically if you can see it, that just VDS would be equal to VDD minus IDRD, so that part just comes out here. Okay, so this is the VDS and this is my IDRD. So just comparing, we can say that my VDS is equal to my minus IDRD, right? VDS is equal to minus IDRD, and we can say that my ID is equal to GM VGS, right? So comparing these two, we can say together that my VDS is equal to minus GM VGS into RD, right? And from there we can say that my VDS by VGS is equal to minus GM RD. This is known as my AV, or the voltage gain. Okay, and if you just take the resistance of the MOSFET also into the picture, just it happens in parallel, so the AV practically it can be written as minus GM and to RD parallel R0, where R0 is the resistance of the MOSFET. In the next video we'll explain with the small signal analysis why this equation comes into the picture. I hope you have been able to understand the transconductance formula, and from there how the voltage gain comes. Thank you for watching the video. Please subscribe for more such videos. Thank you.